All right, so 5.39a, where we're going to start. You can see we don't have any hydrogens attached to the chiral center, but we can order the groups in terms of their priority. We have the hydroxyl as being highest priority. We have carbon-carbon on both of the ethyl and the methyl. We know an ethyl is going to be higher priority than a methyl because it's a longer chain. And this carbon here is attached to a carbon, hydrogen, hydrogen. And this carbon is here is attached to oxygen, oxygen, carbon. And so this will be our second highest priority group. This would be our third highest priority group. And this would be our fourth highest priority group. So there's a couple of ways that you could solve this, okay? Since the methyl is the lowest priority group, but it's not coming out towards us and it's not going back into the page, one way would be for you to imagine yourself looking at this bond going from the carbon to the carbon on the methyl, and then to evaluate, the methyl is going backwards if you're looking from this direction. That's one way you could do it. Another way that you could do it would be to swap two of the atoms. You could swap two, and then that you'd have to reverse the stereochemical configuration. That would work, okay? So we could do either way. If you were to look down the bond, the way that it's written, what you would see is you would have your ethyl group over here. You'd have the hydroxyl group over here. The methyl group is in the back, so there's nothing but protons coming out in the back there. And then here you'd have the CH2, and then you'd have the carbonyl like this, okay? So then you're going from your highest priority group, so 1 to 2 to 3, so you're going in that direction, which is S. Okay, so that's one way of doing it, would be to think about it in terms of a Newman projection. The other way is to redraw the molecule, so we could do that too. So we'll just redraw the molecule. I'll draw it in green. And what I'm going to do is I'm going to swap the methyl and the hydroxyl. So if I have my ethyl group here I'm going to put the methyl group in the back, and then I'll put the hydroxyl down here. Well, then we have 1, 2, and 3, right, like that. And so we'd be going sorry. Sorry, I made a mistake here. Yeah, so I'm going like this, 1 to 2 to 3. Yeah, that's right. Which is clockwise, right? So I reverse it, and then it is S. So sorry, I was right. Anyhow, so either way works, and you end up with an S configuration for that stereocenter. The next one's a lot faster. So we just have an amine on the second carbon here. We can start by putting the hydrogen coming out towards us. The hydrogen is going to be lowest priority. The nitrogen will be highest priority. This would be second because it's an ethyl. This is third because it's a methyl. So we're going from 1 to 2 to 3, which is clockwise, but the hydrogen's coming out, so we're going to reverse it. So it's not R, it is S. The next one, we have a chlorine, which is going to be our highest priority. We have a hydrogen, which is going back into the page like this. So we have 1, we have 4. These two carbons are identical. They're both attached to carbon, hydrogen, hydrogen. But once I get to this one here, it's attached to carbon, carbon, hydrogen. And this one here is attached to carbon, hydrogen, hydrogen. And so this is my tiebreaker. That means that this is my second highest priority group. This is third. So I go from 1 to 2 to 3, which is clockwise. Therefore, this stereocenter is R. Let's take a look at F. This is a Fisher projection. All right, so 5.39F. We'll start with this one that I'm highlighting in yellow. At the top, we have the hydrogen, which is lowest priority. We have the oxygen, which is highest priority. This carbon is going to be second highest priority because it's attached to oxygen, carbon, hydrogen, whereas this one is attached to HHH. So this takes number 2. This is number 3. So we go from 1 to 2 to 3, which is clockwise, but we reverse it. So this stereocenter is S. So I'll erase all this stuff and we'll write S next to that. So this is S. And then for the one on the bottom, we have the hydroxyl's number 1, hydrogen's number 4, this is number 3, this is number 2. We go from 1 to 2 to 3 like that, which would be R. We reverse it. And so this one is also S. So both stereocenters are S. The next one I wanted to look at with you is 5.44. Just let me find it here. So 5.44, which deals with the following pairs of compounds and determining the relationship. So it's going to take me a second to write them down here. So this is 5.44. I'll start by drawing the two compounds in A. So we have an aldehyde at the top. I can just copy and paste this and just manipulate it, or modify it, I should say. So I'll paste that over here. Okay. And on the first one, we have our hydroxyls here and here. And then on the next one, we have our hydroxyls here and here. Like that. Could anybody tell me what the relationship between the two compounds in A would be? Yeah, they're diastereomers, aren't they? Right, because I have these two, they have the opposite configuration. So it's like those two are switched. However, this stereocenter here has remained the same, hasn't it? And so we have, again, a mirror image here, but here they're different. And so these are diastereomers. What are diastereomers? They're stereoisomers that aren't mirror images. What about B? What would be the relationship in B between the two compounds in B? Yeah, exactly. They're enantiomers, right? Because you can see that I flipped this dash to a wedge and I flipped this wedge to a dash. Yes, absolutely. So these would be enantiomers, enantiomers. There we go. What about C? What would be the relationship in C? And I'll try and draw these the best I can. Yeah, they're meso compounds, right? It's a meso compound, but the question is, what's the relationship between them, right? Yes, this is a meso compound here. This is a meso compound here. But what's the relationship between those two compounds? Are they diastereomers? Are they enantiomers? So yeah, so they're not enantiomers. These two are in fact identical. Okay, if you were to take this molecule, let's say, and you were to rotate it 180 degrees, okay, if you were to flip it like on that hinge, you would end up with molecule in reverse, but you'd end up with both of these methyl groups pointing out like this. And so these two compounds are identical. All right, identical. Another option is you could evaluate the stereochemistry at all the stereocenters, but I think it's faster to just manipulate the molecule the way that I did it. And then if we look at the last one are two bicyclic compounds. I'll be honest with you guys, these two are mirror images of each other. It's pretty hard for me to draw mirror images of bicyclic compounds, but that's what they are. And so since these are mirror images, okay, so we'll put here mirror images, therefore they are enantiomers. Okay, not that easy for me to represent, not that easy for me to draw, but hey, gave it the old college try. All right, let's move on to question 5.47a. I wanted to take a quick peek at another Fisher projection with you. So this is 5.47a. 5.47a. So we draw out the compounds. We got 3 stereocenters. All right, we got 3 stereocenters in 5.47a. I'm going to give you a second to try it in case, or if anybody could tell me what the stereochemistry at the first one, the one that I have highlighted in green. Give it the old college try. And remember, this is a safe space. Just do your best. All right. See, one of my students says R. Oh, mute that. All right. I'll give it another second. Yeah, okay. I got everybody saying R. Good, good. I think you're right. I tend to agree with you. Let's try the red pen here. So I'm going to go a little faster now. The hydrogen is lowest. The oxygen is second, or first rather. This is second. This is third. So we go 1, 2, 3 like that, which is counterclockwise. We flip it. So this would be an R stereocenter. Let me delete all this spinach here. If I go to the next stereocenter, I'll highlight it in yellow. We have, I'll use the blue pen. The hydrogen is going to be lowest. Oxygen is going to be first. This carbon is attached to oxygen, carbon, hydrogen. This carbon is attached to oxygen, carbon, hydrogen. We don't have a tiebreaker. So we go to the next one. This is oxygen, 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 and this one is not. So that means that this is going to be the second highest priority. This would be third. We go from 1 to 2 to 3, which is clockwise. We flip it. And so this stereocenter would be S. Okay, I'm just going to erase some of this spinach here. There we go. And then if we look at the last one, I'll use the red highlighter for the last one. For this one, we have the hydrogen, which is lowest priority. Oxygen is first. This carbon is attached to oxygen, carbon, hydrogen, whereas this one is attached to oxygen, hydrogen, hydrogen. So this will be second highest. This is third highest. So we go from 1 to 2 to 3, which is counterclockwise. We reverse it, and it is R. So this is R. So we have R, and then we have S, and then we have R for this one. All right, we did it. There we go. Not too bad. So that's Fisher projections, RSR. Yep, absolutely. R, S, and R, like that. There we go. All right, well, I wanted to look at one more problem. Getting pretty late in the day here. We've covered a lot of organic chemistry in a day. 5.37, I wanted to take a look at A through D. So let me find the question here. 5.37 is just a quick question where we try to identify the number of stereoisomers expected. So this is question 5.37. Let me jot down the first one. 5.37, and the compound is this. Okay, we have a hydroxyl here, we have another one here, and we have another one here. Okay, It's asking for the number of possible stereoisomers. I'll give you a second to think about that one. All right. And then let's skip D because we already kind of did that one. Let's do E. This one's a little trickier. All right, here we go. Did I put a double bond in there for nothing? There we go. I was like, that doesn't make much sense. All right, so 5.37a. Yeah, the total number of possible stereoisomers in A, yes, absolutely. I think it's 8 because what? We've got 1, 2, 3 chiral centers. We remember that 2 to the power of n is the total number of possible stereoisomers, or it's the maximum number of possible stereoisomers. I was trying to select this, just this part here. There we go. So move it over here. So we have 2 cubed, which is 8. So there's 8 possible stereoisomers. We only have meso to worry about when we have an even number of stereocenters. So here we have an odd number. What about B? In B, we have how many stereocenters? We have 1, 2, don't we? But we actually looked at B earlier on, and we said, well, if you put 2 to the power of 2, that equals 4, but you have to subtract 1 here to give you 3. Why? Because you can end up with a meso compound here, where you could have the 2 hydroxyls like this, and we have a plane of symmetry. So we end up with 1 meso compound in this case. All right. And the next one, did anybody get C? Okay. Yeah, how many chiral centers are there in C? There's no plane of symmetry in the molecule, that's for sure. But how many chiral centers do we have? I see that there's one here, there's one here, there's one here, and there's one here. Those are the 4 chiral centers. All right, everything else is either a methyl group or a methylene. Everything else, this is a methylene, this. I missed a methyl group, didn't I? There's also a methyl group here. Okay, so those 4 carbons are all chiral. Methyl can never be chiral, right? Because a methyl has 1, 2, 3 hydrogens attached to it. So since they're all equal, they're all the same, this can never be chiral. So a methyl group can never, ever be a chiral carbon. The same reason as CH2, a methylene could never, ever be chiral. Okay? These 2 groups can never be chiral under any circumstances. So with that in mind, we've got 2 to the power of 4. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So we got 16 possible stereoisomers. Here we have an even number of stereocenters, but there's no plane of symmetry anywhere in this molecule. So we would have 16 stereoisomers. What about E? Could anybody answer E? I'll just give my students a second here. Yeah, well, how many stereocenters are there? All right, we have a stereocenter. Where's my highlighter? We have one here, and we have one here. So you might think that it would be 2 to the power of 2, which would be 4. But since there's a plane of symmetry down the molecule, we're going to subtract 1 for the meso compound, and we would end up with 3. Right? If I just draw the skeleton, okay, if we just Didn't mean to do that, but anyhow. If we draw the skeleton like this, right, I could have this hydroxyl down, this one coming up. I can have this one going down, and I can have this one coming up, and then I can also have a meso compound where they're both going down like this. So that would be a meso compound. So the answer is 3 stereoisomers in this case. All right, here we go.